Good morning, everyone. Good morning. A warm welcome to ECTC 2025. My name is Florian Herold, and I am your General Chair. ECTC 2025 is a flagship conference of IEEE Electronic Packaging Society. Today really marks the culmination of months of hard work and collaboration. We gather here today to express our gratitude to all of those who have made this event possible. First and foremost, I would like to extend a big thank you to our sponsors, whose generous support has been instrumental in bringing this conference to fruition. Your commitment to our shared vision and your investment in our community has allowed us to create an exciting experience for all. And the monitors just went off. Thank you. And obviously, I want to express my sincere appreciation to our exhibitors who showcase cutting-edge technologies, innovative products, and groundbreaking solutions. Your presence adds tremendous value to this conference, creating opportunities for engagement, networking, and collaboration. I want to express my deepest gratitude to our esteemed speakers and panelists who have traveled from far and wide to share their expertise and insights. Your wealth of knowledge, research, and experience will inspire all of us, setting the stage for meaningful discussions and excellent learning. To the technical program committee volunteers, your tireless efforts in reviewing our papers, organizing our sessions, and ensuring the highest quality of content have been instrumental in creating an outstanding program for our attendees. And of course, a warm thank you to each and every one of you today. Your presence and active participation are the lifeblood of this conference. Your enthusiasm, engagement, and diverse perspectives will shape the discussions and interactions over the next few days. Please enjoy this excellent conference ahead. Let me give you a round of applause really quick. Before we start, a few logistical items. Please install the app. The entire program is up to date, obviously. We also have a nice messaging platform for networking. Finally, this is very important. After the keynote speech, we will have a Q&A session, and I will use the app and the live setting under the keynote session to be able to answer questions. Now, without further ado, it's my great honor to introduce our keynote speaker, Sam Nasviger from AMD. Really quick, I would like to give Sam is SVP and Corporate Fellow at AMD, responsible for technical strategy and product architectures. He has been the lead innovator behind many of AMD's products. Thank you, Sam.
Thank you, Florian. Well, I'm super pleased to be able to be here in front of you all. It was 2020 and a very different time, and not in any place in particular that I spoke last time. And AI was barely on our radar. And now for many of us, it consumes most of our waking hours. And so that's what I have the privilege of talking to you about today, are the challenges ahead of us in the AI era, and in particular, how we can efficiently meet the exploding demand for AI compute. It's the most exciting time ever in my 37-year career as a technologist. So the fundamentals that drive this demand for compute are that bigger models are smarter models. And the explosion in parameter counts and compute required to train these models has been going at an unprecedented rate. Now, you've seen graphs like this before, but it's such an extraordinary inflection, it's worth repeating. 4 to 5x per year, the much vaunted so-called Moore's Law was about 1.4x per year, right, doubling every 2. going at 4 to 5x per year is an extraordinary exponential, and there's actually really no end in sight. And you can see even, this year at the end of this chart, we are requiring an exaflop running for a year in order to train the most sophisticated frontier models. Now, obviously, a year's worth of training, that model has become obsolete by the time it's complete. So we need a lot more than an exaflop in a supercomputer to do that training. And this demand is continuing right through. And so, we can ask ourselves, is this a durable trend? We are all skeptical engineers. We look at this stuff. We've seen bubbles before. Perhaps we've gotten a little cynical. So that's the big question are the economics that drive these trends sustainable and durable? So I want to run through just a few examples that have convinced me that that is the case. So I'll start with the medical field. And this is just barely starting to be tapped. It's in various headlines around diagnostics and patient consultations. But if you think on the diagnostic front, the potential for an AI that can ingest a patient's entire medical history, their medications, even their genome, and compare that situation with their ailment to all the other patients with a similar profile and the outcomes of those patients' treatments, and provide a very specific diagnosis and medical recommendation. There is no doctor in the world that can perform that sort of analysis with that breadth of data and provide that specificity of a diagnosis. The power is immense. And the ability for robotics to impact surgical procedures. And then there is drug discovery, and this has already taken off. AI has tremendous capability for understanding the entire molecular search space of drugs and how they have impacted biological behaviors and their impact to diseases and pathogens and which ones are benign and have side effects, and process that and produce meaningful ideas on the particular type of drug and DNA that will treat an ailment. So medical applications are going to be immense. And then robotics, and we're really just getting started. Industrial robots have been a fixture for a long time with very limited range of motion, very specific actions. But what's going to transform the field of robotics is combining the robotic mechanics with the ability to process sensor information in real time and couple that with a digital twin representation in the cloud where the robot is modeled and trained and can absorb the information and the training that's provided by other robots in other environments. And so to be able to respond in real time and make useful decisions based upon the sensor feedback is going to be completely transformative. And the economic impact of intelligent robots that can adapt and respond to their environment and perform tasks that humans perform, but do it 24/7, the opportunity is mind-boggling. And it all depends on AI. And the final field that I'll mention as a motivational supporting statement for why AI is huge and durable is, of course, AI for science. Science is about making sense of the world of data with math and equations and applying that to physical problems. And that is a great description of what AI is great at. Absorbing climate patterns and understanding crop yields based upon soil types and the particular characteristics of the pests in that region. So in agriculture, the opportunity is going to be huge. It's like having an omniscient farmer who understands 100 years worth of weather behavior and the response of his crops to particular fertilizers, and can come up with the exact right variant to plant for this year, the right pesticides to use, the right genomic variant to use, and improve yields and durability of those crops. And biomedical, material science, the opportunities are amazing, and it's super exciting. As at AMD, we're involved on the leading edge in the supercomputing field. We sourced the hardware for the top supercomputers, and the way AI is transforming the supercomputer, high-performance compute space is amazing. So hopefully, I've made a good case that the demand is durable, and those exponentials are going to go as long as physically possible. So it's important then to understand, how is this AI field evolving? And this is moving at a faster pace than I have ever experienced in my 37 years in the industry. I used to think I worked 10, 15 years ago in an extremely fast, dynamic, high-speed environment, technology constantly evolving, but it's nothing like we see today. So I hope I could give you a couple insights into trends that I see in the evolution of AI, and they affect how we plan for our future technology development. So the first one to note is this large model training. The blue bar on the left is what's driven AI, the ChatGPTs and the Geminis, to achieve their amazing capabilities, ingesting the entire universe of internet data and training the model. But we've run out of data. The high quality textual data has been completely consumed. Now we can do multimodal models looking at photographs and videos, but it's much lower quality. There's much less information per bit in that data set. So the way AI is getting smarter is through approaches called post-training and test-time compute, or chain of thought reasoning. And this is where models check each other, generate synthetic data, and iterate on a response, and produce a much more thoughtful outcome. So we've hit the data wall. Pre-training is reducing in importance. Does that mean that compute demands are going to diminish? The emphatic answer is no, because of the chart there on the right, that the intelligence of these models, which is what makes them so valuable and indispensable to our future, improves with the log of compute invested. And of course, that means exponentially more compute for a linear return in intelligence. And every increment of intelligence is hugely valuable. Going from grade school math to graduate level understanding is an incredible gain, but it takes 2 or 3 orders of magnitude more compute. So the demand for compute is going to continue to escalate. And what that's done is drive down costs. And this is what our industry is super great at, right? We refine our manufacturing processes, we generate higher and higher volumes, get the yields up, and costs go down. We use software and tuning and new revisions of the silicon. So each one of these lines is a constant intelligence level on a given benchmark. So like the blue one is MMLU, greater than 42%, and the cost has dropped by over 10x per year for the same level of intelligence, which is amazing. And the paradox here is that being cheaper doesn't mean people consume less. Jevons paradox says that when a desirable quantity becomes cheaper, demand for it in absolute dollar value of consumption increases. Sort of like when cars become a lot more fuel efficient, more gas is consumed because people don't drive less, they actually take advantage of their higher mileage cars and go further. And it's similar with this inference. So we have a huge and rapidly growing demand for AI. And the next, and the final thing I wanted to hit on here, which is quite fascinating to me, is the pursuit of AGI, or artificial general intelligence, which is kind of the pot of gold at the end of the rainbow, right? Gotten a lot of airtime. And so we should ask ourselves, how do, people don't know how to measure this for sure, but we keep generating new benchmarks. And, LLMs are amazing at regurgitating knowledge, answering test questions, and identifying patterns. But we have found there are a lot of benchmarks that are easy for humans that LLMs just are stumped by. For instance, simply filling in a yellow square in the gap in the pink ones ends up being really hard for a lot of these models. Now, the new test time compute chain of thought models can do better, and we get excited, but then we come up with a new benchmark. It's like, hey, if it has 3 holes in the shape, color it green. If it has, 1, color it yellow. Humans are 100% on this. Easy to do. LLMs completely fail. The test time compute models like O1 from OpenAI do a little bit better, but they cost a lot more. So this is the progression of intelligence capability. It's fascinating to watch, and we're going to continue to develop new models, and the LLMs get better and better. As they solve these human-specific problems, they become more human-like and more useful to our world. But it all requires compute. And compute creates demand, and it creates economic activity. And as the final overview here of why we are in the midst of a very durable development in our industry, these charts on the left, the dollar numbers on the right are huge, but it's really useful to look at the projections for CapEx spend for the top 8 AI companies. And that's what's averaged out on those lines. And the orange line is the prediction over time for from back in 2023. And it went up and to the right, it was big. But then in 2024, the averaged CapEx outlay for these companies was projected to be on the red line. And in 2025, it moved up to the blue line. So the projections for spend are actually increasing. Model usage growth, inferencing, everything else isn't going down, it's only increasing. So a super exciting place to be. So now we got to get into the technology, right? What does it take? This demand is there, it's growing, compelling applications. How do we source the demand? What are the challenges we as engineers have to solve to exploit this opportunity and all that AI can bring? The improvement year over year for just GPUs, and I focus on GPUs, it's something we develop at AMD, I know well, and we've been doubling compute floating point operation performance per year at a very consistent rate. And that's quite an exponential. And it's been driven by better algorithms, implementations, and the, of course, progression of silicon speeds and packaging technology, packing more and more silicon into a given package. Then we've been adding on to that lower precision math. And this is critical because AI can exploit fewer bits per number very effectively than traditional scientific compute. And of course, an 8-bit number, it consumes half the bits of 16 and 4 on down. And multipliers for these low formats become super simple, just a few XOR gates rather than big arrays of devices, right? So the software, hardware co-design to exploit these low precision formats is a huge open search space that's produced tremendous value already. So the rates of improvements on flops are extraordinary, and we have to feed the compute with a consistent bytes per flop. So the HBM, which is the memory style of choice for most of these big iron compute devices, has been feeding them, and we've been demanding, commensurate with the flop improvements, greater than 2x per 2 years. And actually, those low-precision math formats, they consume a little more than half the bandwidth per flop. So memory bandwidth demand is extremely steep, but despite the best efforts of our friends, the DRAM vendors, the HBM stack itself has only been improving about doubling every 4 years. So of course that means if we have twice the rate of doubling of bandwidth demand versus the memory itself, we have to put down a lot more stacks of memory. And so that's what you see happening in the industry. And that means bigger and bigger modules to host these HBMs stacked up next to the silicon that consumes that bandwidth, creating ever bigger and more challenging to manufacture and yield silicon packages. And not surprisingly, the power increases commensurate with the flops and the bandwidth. Despite the best efforts of our silicon technologist friends, the energy per operation improvement from each process node is diminishing. And since we're doubling every 2 years, there's no way that could keep up. And our power has just taken a much steeper upward turn than in the past. So we have to deliver power into these devices, and we have to get the heat out. And the industry is moving towards direct liquid cooling and other cooling approaches because there's no other way to get the heat out. So you may ask, why don't we just split these devices up? So the memory isn't keeping up. Well, heck, let's just do a lot of small little compute devices. They'll be a lot easier to cool, lower power, and distribute them out. And that's a much smarter approach. Why are you guys going for the chest-thumping huge modules and packing everything in? The answer is that energy of communication increases exponentially with distance. And that's really the fundamental. So when we're on the left side of this chart and computing in the device, the energy to move a bit back and forth from the memory or from the cache to the floating point unit and back and to iterate on a result is dramatically lower than you have to iterating on a result across devices or in the rack. So we have factors of tens and hundreds between different levels of communication. So maximizing locality is the key to efficiency. And that factor is what is driving our focus on these big compute modules, tight integration, and the packaging technology to make that possible. So the net takeaway is that power is limiting our performance. It's inexorably increasing as demand for AI and the compute goes up and as the technology scale factors cannot keep pace. So you've seen all this in the news, gigawatt data centers and the renewed interest in nuclear power and all aspects of power consumption. We're going to be up in multiple gigawatt regimes in the future. So let's dig into where that power is going and how we can bring it down. The data center power consumption is driven by basically compute, communication, and overhead. We want the compute to consume the vast majority of the data center power, if possible. But we always have to communicate between these devices. And the reason we're building these giant data centers with these big racks with tens to hundreds of huge GPUs connected together is because that's the most efficient way to run these AI programs. They have to exchange data, and the more memory that can be shared between multiple devices, the more efficiently these models can iterate towards the final result. That iteration requires communication, and that's the slice that you see there in the middle. And then between racks is the scale-out network computation that typically today is done with optical interconnect. And then we have the data center overhead on the top. So our goal is to drive down each one of these elements: more efficient compute, more efficient communication, reducing overhead. So the advanced packaging, and this is what I'll get into in more detail now, is just fundamental to how we can meet this demand in as efficient a way possible. 2.5D foundational, we've been doing that for many years. AMD pioneered this with HBM over 10 years ago in the gaming space, actually, before the AI era, but it has proven foundational to growing the AI compute. 3D is something I'll talk about more. Obviously, tighter integration of components with minimal distances, low communication overhead is going to be key for those huge modules I talked about. Inevitably, we have to communicate between devices in that scale-up domain with the shared memory. Electrical has gone far faster than I ever deemed possible. 10 years ago, if I thought we were discussing 200 or 400 gigabit per second over copper, I would have thought, yeah, you're crazy. It's just amazing how we've squeezed the copper and figured out how to signal over those lossy channels. But it is running out of steam, and optical is the future. So integrating this is completely essential. And as you saw that power curve taking a steep upward trend, well, as power increases, current increases, and power delivery becomes a huge challenge. So a lot of exciting opportunities in that space, and I'll talk a little more about it. And getting the heat out is one of the most exciting and fascinating challenges. And with kilowatts being pumped into these modules, the hot spots, the cooling technology is moving very rapidly. So let me talk about each one of these areas in a little more detail. And the first thing to note is the 3.5D and why it's so valuable to our industry. And the fundamentals boil down to the cost of communication, which is what I hit on before. It's why we're packing as much as we can into a module, right? So, on-package communication, pretty good. It's a lot better than going off-package. 2.5D is even better. We can get a lot more bits per joule of energy. But with 3D, we can dramatically reduce the energy cost of compute. And since power consumption is the currency of compute and the fundamental limiter to how far we can scale it, if we can exploit this capability, we're going to produce higher performing, more efficient devices that the world can consume more of. The other very attractive aspect of 3D is that we can pack more silicon in the module. Once again, locality is king, right? So if we can get more high-performance silicon co-located in a package device, we have a high-performing device, provided we can cool it and get the power in. The ability to manufacture these large modules is constrained by warpage effects, stuff that you all know very well, warpage, yields, all of the factors that constrain how large we can produce these. So if we can 3D stack our silicon, we can get more compute into that same footprint, the same yield with the same constraints. So about 2x the compute area, yet another motivator for going 3D, low communication overhead, higher density of compute. So let me talk a little bit in detail. Now, this is last year's product. We're coming out with a new one to be announced in June. And it actually looks very similar to MI300 in construction. So this is very relevant to the latest and greatest AI GPUs from AMD. So to review some of the capabilities we've packed in, we have partitioned the die into multiple, the big compute device into multiple pieces of silicon. And we did that because that improves yields and it improves modularity. So we can produce multiple product variants from the same tape outs if we know how to connect them up efficiently. So we can pack CPUs into here, we can pack compute devices in. Obviously, the 8 HBM packages are critical to provide the memory bandwidth. We have cache and all of the interconnect components to communicate between multiple devices. The stack-up sandwich looks like this. It's remarkable how we've been able to pack so much into one device. And you know, the cartoon on the lower left really can't do justice to the what I consider just a beautiful cross-section there on the right of how all this comes together. You can see the C4 bump on the bottom, the micro bumps above the CoWoS silicon interposer layer in the middle, and then you have the through silicon vias for hybrid bond connecting the two die in the middle with the silicon carrier on top. And the green layers in the left cartoon are the active silicon. And note how we have on top what we call the XCD. That's the compute device, which does all the math and generates the most heat. So we have the active devices for that XCD at the very top of the stack, right next to the heat spreader, better for thermals. So putting all this together, it's a very elegant construction that solves many problems. We have direct high-speed connections to the bottom die, which has the cache and the communication network on chip that then goes to the high bandwidth memory, which is 2.5D connected. So we can move a lot of data on this device in a very efficient way. And that's what I've plotted here. When you tabulate the connectivity and the bandwidth in the diagram on the right, we have terabytes per second communicating between the 4 I/O die, and each of those 8 XCDs can consume 2.1 terabytes per second vertically through the hybrid bond through silicon vias. Communicating that much bandwidth through even an advanced package 2.5D connection would cost almost 100 watts, which is what I've shown on the chart on the left, whereas it's less than 10 watts through hybrid bond stacking. This sort of power-efficient high bandwidth is what's going to continue to drive 3D stacking as a key enabler for AI compute. Another thing I want to spend time on, because it's critical to understand, is that software has the ability to dramatically improve the power efficiency of our devices. So we all work super hard designing the most efficient silicon, the most amazing packaging and low power interconnects, but if software abuses them, we're going to end up with power inefficient compute. And so that's what I've wanted to show here, is that we have the ability in this device to partition it into multiple segments. And those segments affect the cost of communication. If we can have data co-located on a fraction of this big module, and let's say most of the communication occurs locally to the nearby HBMs, and only necessary ancillary communication goes to the others, we have a lot more power efficient compute. So these we call NUMA domains per socket, or NPS domains, and software has to be aware of the construction of the device in order for this to be effective. And so to illustrate that a bit further, we have the pyramid of connectivity there on the right, and you can see the compute devices are the top layer in the gray boxes, and then they go to their first level of cache, second level of cache, last level of cache, and HBM. And we do all of these caching levels to improve locality and amplify bandwidth as we move up. And that makes a lot of sense because communication gets dramatically cheaper as we get closer to the compute devices, which is what I've shown there on the right. So what we need to do is to inform software of this hierarchy and get it to map the matrix multiplies for given segments of the workloads to quadrants or smaller segments of this GPU device. And when we do that right, we can save over half the power. And that's a huge saving. You think about what it takes to cut power by a factor of 2 through silicon engineering or package innovations. It's heroic efforts and hundreds of engineers and exotic equipment, right? So this highlights why the hardware-software co-design aspects of our effort are so critical. We have to work closely with the hardware folks to understand the software folks to understand the hardware so they can map the algorithms to it properly. So I'll look forward now a little bit. We have plenty of challenges as we see the growth that we have to feed in the future. And power delivery is near and dear to my heart. And I've illustrated here today's devices, and you can see top right the topology on these big compute modules. So these are, kilowatt plus compute modules today. And so we're talking multiple kiloamps of total current that has to go into the silicon device. The stack of blocks on the left and right of those diagrams, which are MI300, MI250, are the voltage regulators. And so, of course, if you look at the bottom, those things are stacked left and right. Well, then they have to deliver the kiloamps of current horizontally through the package. And there's resistance in the package. There is resistance in the bumps between the power blocks in the device and the BGA package and all the other elements in the path. That costs I²R power. So current goes up by a factor of 2. I²R losses go up by a factor of 4. And pretty soon, we are in the untenable domain of generating a ton of heat in the package and wasting those precious watts, which we really need to go to compute, because power is what's limiting our growth in this industry. So we're going to have to move the power delivery underneath the compute devices. That's the obvious and most direct route. If we can get those voltage regulators into the blue module or underneath the blue module, we have much lower resistance in the path to compute, and we have better regulation of our voltage and a more efficient compute device. And there's a lot of great and exciting work going on in this field, but it's absolutely essential to continue our scaling. Thermals, I've already mentioned, today's air cooling can, we're managing to cool up to 1,000-watt devices with high-speed fans. And that's on the left there. And I have to note that, I total up these rack-level power consumption budgets and what we need to work on, and fan power is a frighteningly large number, like 20% plus of the total rack power. So I talked about I²R losses costing 10 to 20% of power. Fan power can do the same. So now we got 40% of our power just for delivering current and extracting heat. That's obviously not the way to build an efficient compute system. So that's what's driving the relentless move to direct liquid cooling, which has some power overhead from pumps and condensers, but dramatically less than high-speed fans with huge heat sinks. And so liquid cooling, absolutely critical, and it's a driver not only of enabling higher power modules, but of improving the power efficiency of our data center, because it produces less waste heat. Then there's the optical interconnect requirement, and I touched on this already, but the days of electrical are indeed in our rear view mirror, at least by the end of this decade. And part of that is actually related to power. I mean, we can signal faster. It's just the distances we have to travel, or we're able to travel with 400 gigabit per second, are very limited. And that means we need to have retimer devices put down on the boards to boost the signal amplitude and recover the signal. And retimers cost power. They cost as much power as the original driver on the device. And so it becomes impractical to signal at those rates, and very expensive as well. So optical is, it's going to get cheaper over time, but it's not cheap right now. It's fiber attached units are complicated, and there's a lot of sophisticated devices. We need lasers in the system, figure out where to put them. They have temperature limits. So there's thermal interactions, a lot of exciting challenges to overcome with this technology. And getting it into the volume where we can reliably produce millions of these and have them operate for years on the world's most complex problems, it's a big challenge. And it's something many of you in this room, I'm sure, are engaged in. And I also view optical as a big opportunity for improving the efficiency of our compute modules by reducing the energy to communicate between devices even on the same large package. So lots of exciting work ahead in the optical domain. The other area that I see huge opportunity is continuing the move to reduce the memory bandwidth power consumption. So I talked about how our demand for memory bandwidth is continuing up and to the right, outstripping what the memory stacks themselves can produce. And the energy for memory is very high. If you remember that pyramid chart, it's hundreds of times more than local connectivity through a 3D stacked hybrid bond interface. So we need to solve the problems around the 3D integration of high bandwidth memory. And there are a lot of problems here. The thermals are one obvious challenge, because not only are we increasing the absolute power of our module, but now we're increasing the power density by putting more devices together. And we are also, of course, creating power delivery challenges. Those currents I talked about are very high, and all we have are through silicon vias to deliver current. But the carrot at the end of the stick is that low energy per bit to communicate vertically. And so there's tremendous economic motivation to solve these problems and do these tighter and tighter levels of integration. So scaling up to meet the AI challenge is the grand challenge of our day. And the problems are exciting. They are daunting. And the amount of innovation in this field is escalating, driven by the economic demand and the huge potential of this technology to transform our lives, to improve the world in so many different ways. The growth of these compute modules is driving the need for much tighter 3D integration, higher bandwidth communication between them, the power delivery, and the heat extraction. I personally am super excited about the opportunities ahead of us and the tremendous power of our industry to collaborate together and solve these problems for the betterment of our world. Thank you for the chance to speak today.
Thank you, Sam, for a very exciting talk and very inspiring. Thank you again. We are now going to take questions from the audience. There is a microphone in the middle. And please, if you want to use the app in the live section of the presentation, I will be able to relay the questions to Sam. Come on. Thank you.
Yeah, thanks.
Yeah, thanks for the great presentation. My name is Junro Young from Corning. So we're talking about this bigger and bigger the packaging. Based on my understanding, I don't think we can make package size bigger than rack size because we cannot accommodate in the system. So assuming the packaging size is getting bigger and bigger, do you think that bigger package is still kind of the better way to improve the system performance, or do you see any other kind of the mass way to improve the system performance better?
Yeah, good question. So I tried to communicate that hierarchy of the cost of communication. And that's the fundamental factor driving the value of large packages. And of course, the bigger a package gets, the higher the cost of communication from one side to the other. And so there are diminishing returns, right? And that's where 3D becomes particularly valuable, because we can go vertical and we can get more silicon into the same size at lower cost of communication. And if we can get memory into that same vertical stack, we have an even more compact, efficient compute module. And so to your question that, are there better ways than the size of the package? Yes, because we get the package beyond a certain level, and it's no better than two packages with, say, an optical link between them, right? So those are the sorts of problems we're going to have to grapple with, because it's all about the efficiency of communication and how the software maps the problem to perform the compute task with the least energy possible. So we all need to be thinking about the energy of compute and the cost of communication in our choices around technology development, because that's what's going to drive the value.
So then can I interpret your answer as the future architecture more like the inter-package, the communication with a 3D stack, probably another kind of the future direction?
It's going to be a critical part of the future direction, yeah.
So at some point, this bigger package, the increasing package size will stop at some point because of the...
It will, yes. Yeah, we will hit a point of diminishing returns where the cost and the manufacturing challenges will not be worth whatever energy savings remain.
And that is based on the intra or inter-package, the efficiency should be better than on-package energy efficiency or the
Correct. Yep, provided the software is smart enough to map it.
Thank you for the great question. I'll ask one really quick, Sam. You talked about AI for medical applications, robotics, and science. Do we understand the target metrics and what the chip should look like 5 years from now to be able to, for example, have fully intelligent robots, and where you need to go? What is the energy per bit you need to achieve? What is the data rate?
Yeah, no, that's a great one. I mean, the field of robotics, in particular humanoid robotics, the technology challenges are pretty immense, right? I mean, there's the actuators and the mechanics of these machines, and their ability to sense their environment and then respond and interact, and tremendous developments going on there. And there's a division of the compute, I think what you're getting at, between what's co-located in the device and what is in the cloud. So we can't possibly include in the device all the compute required for it to respond to all of the millions of sensory inputs it's receiving, and the history that it has to have about how to respond to those inputs. So that's why we need that digital twin in the cloud in some gigawatt data center somewhere, right? That has a much more comprehensive view of the robot's capabilities, environment, history, and how it should operate. So the division, it's going to be fluid, the division between, but there are absolutely needs for low power, highly efficient edge computing capabilities in those devices. Flexible FPGAs are very attractive compute target for robotics. And big kilowatt GPUs, not so much. So that's going to be the realm of the cloud aspect of compute. But yeah, the developments are progressing really rapidly. It's an exciting space.
Thank you. Go ahead.
Yeah, James Liu, professor from RPI. You talk about the 3D, 3.5D integration. I have been working on this for more than 25 years. And actually this year marks the 20 years I coined the hybrid bonding concept. And, we will solve all the problem for 3D integration and reduce the cost. But probably some problems are harder. Can you mention one of the probably most challenging problem with the 3D integration that may take time to solve?
Yeah, that's fine. We've been delivering this in high volume now for like about 4 years with the Vcache solution, initially targeted for our desktop CPUs. Mm-hmm. And that was a real good initial step into 3D because it was an optional performance enhancement to the CPU, right? So we still had a great product without the 3D cache stacked on top, but we could charge more and provide higher performance for devices that used it. And so that allowed us to gain a lot of experience in the manufacturing aspects. And some of them related to yield, some were device degradation effects because we have to thin the silicon significantly. The thermals were pretty exciting because with the thin silicon, the heat has much less opportunity to laterally diffuse than with a nice thick 800 micron chunk of silicon, which is a great thermal conductor, but you cut that down to 10 or less. So thermals are definitely and will continue to be one of the big challenges there. And we have technologies around fine-grained thermal sensors and the ability to monitor and adapt to thermal excursions by reducing activity levels and such. The other big challenge besides heat extraction is, as I mentioned in the talk, is the power delivery, right? So we have these very thin copper pillars. Our silicon devices love to have their own, each IP, wants its own voltage rail.
That's right.
If you force everybody to the same voltage, you end up with a lot of inefficiency. So now we want to chop up the power delivery into dozens of voltage domains, and that means less copper for each one of them, right? So how we generate the power with minimal loss to the device with these high currents is I believe, one of the bigger challenges as well.
So power delivery and thermal management. Thank you.
Not to mention yields and assembly and test and.
Well, you guys can work out. I'm from university, so
Yeah.
thank you.
Yeah, thanks for the question. And actually, can we just talk about this cross-section for a second? What an amazing stack-up, right, that we've seen. Can you talk a little bit about, as a fabless company, the strength of your relationship with a semiconductor foundry and how you both roadmap the future effectively?
Yeah, no, that's a great story. And I do believe it's, our industry has been disaggregating and far fewer vertically integrated companies than in the past when I started my career. And so we end up with extremely strong technology providers in the packaging and silicon space, test and assembly. And AMD's fabless were mostly design engineers. But we have an extremely strong group of folks, some of them here today, who interface regularly with with our semiconductor partners. And as our manufacturing volumes have increased over the years, we've gotten a lot more attention from these important suppliers. And so we can provide input about how they need to shape their next generation technology because they trust our voice to be representative of what the industry will require in the future. So it ends up being a very close collaboration, which is the only way these things work, right? Hard problems are solved by groups of engineers collaborating together, sharing data, bouncing ideas and solutions off. So we've actually been able to develop that kind of a close collaborative relationship with these leading edge suppliers, TSMC, ASE, Amkor, all the OSATs. It's been extremely productive.
Yeah, very nice to keep the ecosystem going.
It's all about the ecosystem.
Okay. Ms. Koyane from Togo University. Now you're talking about stacking of the HBM onto the compute chip. Okay. Basically, the DRAM performance is very strong, rapidly improved by introducing the HBM due to the parallel data processing inside the HBM. Okay, but even use the HBM, the output data of the HBM converted from the parallel to serial. So the eventual data bandwidth is limited by this parallel to serial conversion. So if we can use parallel data from the HBM directly, then we can improve the performance very much. So that when you stack the HBM onto the computer chip, it is possible to use such kind of the parallel data as it is in the computer chip. That case, then you need some special computer architecture to effective the parallel data from the HBM.
I think what you're getting at is compute and memory and the opportunity there. Blurring the boundary between the compute device and the memory device.
Yeah, and 3D integration is very effective to use the parallel data, okay? So that if you can use this parallel data directly in the computer chip, then we can reduce the power consumption.
Yeah. Yeah, no, that's absolutely blurring the boundary between compute device and memory device is an active area of research and a big opportunity. And memory devices aren't very well suited to energy efficient compute, but that compute can be right next to the data bits that feed it. And so there is opportunity, processing and memory. Probably the biggest barrier to exploiting that is software. And one thing I have learned the hard way over many years as a hardware engineer and designer is software is actually harder than hardware. To get the software to change and adapt to a new compute paradigm is a monumental task. But there is sufficient motivation to drive these approaches to exploit more near-memory compute or in-memory compute. So that is absolutely going to be a direction.
That is a good theme of the STCO. Okay? STCO. Okay? System hardware co-design, that's very important.
Yeah, co-design is critical. Thank you.
Yeah, thanks.
Would you like to answer a question about the stock market? We
have the inevitable.
A very nice question. Fantastic talk. Obviously, investment is critical for companies like AMD and others to continue to create, innovate, and exist. With the power of AI, how can we understand the stock market predictions? Volatility is, I guess, important there. Any comments on the future of the stock market?
Can it improve stock trading and balance the stock market?
Or we completely destroy it?
Why is AMD stock price so low? Yeah, I don't think artificial intelligence is any better than humans at stabilizing the stock market. But yeah, it's pretty interesting to see. And that's why I included the durability of the growth patterns in the talk, because investors are trying to make sense of this. Is it real? Who are the winners? Who are the losers? And no one really knows, right? I think, we know, as a company at AMD, it's my job to set the strategy and the investments that we make, those long-term bets for the future. And so understanding those trends, making the right bets, and then sticking with it. So stock market fluctuations are noise. We've made decisions well-informed. We understand the trends, and you low-pass filter all of that stuff. It'll work out in the end. But it all does come down to the economics, and so it's fundamental.
Thank you. Take one question from the audience.
I'm Krishna Chaitri from Corvo. So you mentioned multiple times about the criticality of thermal management to make this technology viable. My question is, what level of innovation is required to make this happen? Does it really require for us to learn how to manage the thermal conductivity, or it requires some breakthrough innovation to come up with some new materials or super cool fluid, something like that? So your thought on that, please.
Yeah, no, good question. So, what technological innovations? As with anything, just like, pushing electrical signaling from what seemed, extraordinarily fast at 10 gigabit per second, all the way up to 100, 200, 400 gigabit per second across copper wires, That is a process of continual improvement and evolving the technology, learning from the iterations of development. And we're going to have the same thing with thermals. Now that, we're way beyond, 20 years ago, I was at the bleeding edge pushing the envelope of our CPU servers to 130 watts. People thought that was ridiculous. 130 watts is like this cooling limit. Well, now we're, kilowatt plus, and we're going to keep pushing that higher. I've seen tremendous progress there, and some of it comes down, liquid cold plates, how fast do you pump the fluid through, what temperature is that inlet water, or do we use refrigerants? Local thermal sensors, like I mentioned, to get the device to be more resilient to thermal excursions, because it's the downstream device that gets the worst of it, right? The first guy preheats the fluid, and if you got multiple, and then data center variation. So the more adaptive our silicon can be, the more resilient it is to heat issues. Then there's the reliability of the device itself. We have to, improve our tolerance to those things. But I think in this industry, our horizon is no more than 5 years, or we're kind of fooling ourselves, right? I see optical on the 5-year horizon big time. I see continued 3D integration as critical. And then on thermals, I think we're at the point where we continue to improve what we know. Microfluidics have proven very, very difficult to deliver a significant improvement over direct liquid because of pressure drop issues and other, flow challenges. So I think pushing what we know today and improving all those dimensions through cycles of learning, we're gonna solve this for the next 5 years.
Thank you. On a similar topic, in terms of technology advancements, it seems like non-silicon technologies are not on your radar at all. Do you think the door has closed to brand new semiconductor materials and transistors at this point, with silicon being so far ahead?
Yeah, graphene and other device. It seems like those keep getting pushed out. Just like gallium nitride was the technology of the future for most of my career, and still is out there. And we're integrating a tremendous number of exotic materials and metals and such to extract more out of the baseline silicon device, the metal oxide, and the new interconnect materials. So, but yeah, there is nothing that I've seen in my limited 5-year horizon that says that silicon isn't going to be the thing for the next 10 years. Yeah.
It's a big challenge for the industry, beyond packaging as well. We have some really nice pointed questions, technical questions on the app. So I'm going to ask a couple, but please come to the stage if you'd like to ask as well. One of them is GPU to GPU stacking. Is this something that is on AMD's horizon to increase compute density?
Yeah, that's a good one. We have certainly looked at it, and obviously super attractive. So you take a GPU or a compute device and stack it on top of another. The cost of communication drops. All the goodness of 3D, we get a higher density. The obvious problems are the ones that I just talked about, right? Power delivery and heat extraction. And you can run the math, and if you cut the power of each one of those devices in half, your power density and didn't worsen. But in order to cut the power in half, we had to reduce the operating voltage, right? So if your nominal voltage was 0.8 and you drop it to 0.6, you get substantial power reduction. Your current went up by 33%. So power delivery got worse, but your heat extraction is largely unchanged, although you have some more thermal resistance in the path. And I could see someone exploiting that sort of a compute stack. Now the barrier in my world is we've already played the voltage reduction card to get the power, get the energy per operation as low as possible in today's devices. So it's going to be really tough to do that again in order to stack two devices, but it's something that perhaps new CFET technologies or gate-all-around would enable in the future. So it's worth evaluating.
Yeah, great answer. We've talked about power and thermal and energy efficiency. Do you truly believe that the scaling of energy efficiency will keep up with AI models? Or you'll always be racing against the newer and newer models? And
yeah, that if you extrapolate that chart I showed with the scatter plot, it is kind of frightening. So we set very aggressive energy efficiency improvement goals at AMD and strive to meet those and generally have. But I did do some math to just look 5 years out on that chart, and we've got great efficiency improvements. We feel pretty good, but that trend is going to dramatically outstrip the efficiency gains by like orders of magnitude, right? So it's a how does that balance out? No one knows for sure. The one thing that's certain is the more efficient we can make our devices, reducing that cost of communication, improving integration, optical, all this stuff, the bigger the market will be, because power is what's going to limit these big deployments. And all the projections are that, our efficiency gains will not be able to fully keep up. So we're going to be steering more of our worldwide grid power to compute, which is good for us as an industry, right? But we got it.
That's right. I think we'll stay busy for the next few years, for sure.
Yeah.
Let's take one more question from the audience.
Yes, my name is LC Chen from Taiwan. Thanks for the exciting lecture about this amazing topic. My question is from one page, you mentioned about the power consumption. The AMD, your company, do a great job for the GPU, HBM, power consumption reduced. What's your idea and plan for the other portion to reduce the power consumption?
Which other portion?
Yeah, something like the system overhead or the scale up.
Yeah, no, that's great. The other portion, so in like the rack, the scale-up domain has switches, network switches, that connect the multiple GPUs together. So we can't directly connect 100 GPUs, with 100 wires. We need to go through a switch to get the bandwidth of communication. So those switches consume a lot of power as well. So that's definitely a target area, improved switch design, and that goes hand in hand with interconnect technology. So making those switches optical, very attractive. And then there's the scale-out switches, which today are Ethernet. We're moving to Ultra Ethernet, and improving the efficiency there. And power management approaches for this communication, because these workloads go through phases. They go through compute phases for tens of milliseconds to seconds, and then they exchange all the weights and activations to go to the next phase of compute. And so if we have power management, perhaps software informed, that can recognize those phases, power off the switches during compute phases, and then reduce power in compute while switching, then we end up with an average power reduction with no loss of performance. So that's one example of approaches balancing communication and compute. And then there's the power delivery overhead. It's like 20+%. There's the cooling overhead, where fans are super wasteful. We want to go to direct liquid, and then the networking, like I discussed. So those are the big focus areas for us.
Thanks.
Yeah.
Thank you. Yeah, I mean, it's really fascinating, right? We talk about optics, we talk about thermomechanicals, power, thermal management, electrical interconnects, truly multidisciplinary, which is really a testament to this audience here. As we wrap up, I'm curious how you like to describe AI innovation, and the future of AI to the general public. So not people who have advanced degrees, but 99.9% of the folks out there. And how do you make them gain confidence in models and in the answers and all of that? Can you comment on that?
Yeah, that's a great question. I do get asked that a lot. And it's not, I view AI as just another tool like, computers back in the 60s, or, the internet in the 90s, 80s and 90s, and AI is yet a more powerful way to extract information and to share information that humans have generated. So it can be used for good or for ill, is the way I describe it. The potential for good is huge, just like I think we'd all say the internet has produced great value for humanity in that knowledge sharing. So it's a powerful tool, but we need to be careful with it. And I'm not going into the ethics and security aspects of AI, but they are real and significant. So yeah, it's like the yin and yang, right, of technology development. But overall, I view it as a force for good.
Well, thank you so much. We are going to wrap up now. Thank you, Sam, for an excellent talk and a great Q&A.
Thank you.
Thank you, everybody. We will have the technical session starting in about 15 minutes.